very good. So it's a real pleasure to be here. Always like to come to Curie and find any excuse to do so. So I was asked to talk to you about, give you an introduction to control theory and then cybergenetics. So cybergenetics is basically the application of control theory to genetic methods. But the first 1 hour of this presentation will have nothing to do with biology. It will be just an introduction to control theory, and I will do this on the board. And then for the last half an hour, I will switch to the slides, to PowerPoint, and I will show you how some of these ideas can be applied in synthetic biology, right? Following the presentation of, nice presentation of the previous speaker. Okay? So control theory. So what is control theory? How many of you know what control theory is all about? Okay, not many. Okay, so basically it's all around us. Control systems are all around us. They're in our phones, they're in our planes, they're in our cars that we drive, they're in our bodies everywhere. And so when they work, you don't even know they exist, right? The only time you know about control systems is when they fail, because usually when they fail spectacularly. You know, planes crash, you get cancer in your body. So essentially, control is all about regulation, and control theory is a theory of regulation. And since biology is also, much of the complexity in biology is about regulation, I think there's a place for control theory in the study of both systems and synthetic biology. Let me start by giving you first maybe an anatomy of a control system. Just to get the conversation going. So usually in control systems, you have a process that you would like to control, usually a dynamic process. So this could be the airplane, it could be a car, and it's a dynamical system, usually nonlinear. So it's described by ordinary differential equations, sometimes partial differential equations, depending on the situation. And so that's what you would like to regulate. And usually this has an input, which we call U, and it has an output that you want to regulate, which we usually call Y. Okay? So this could be, for example, the altitude of an airplane, or the speed of a car, or the position of a car. And this here could be, this is the control input. If you think about the airplane example, this could be, for example, the angle of, deflection angle of a control surface, right? The rudder or elevator or something, right? And this process is often unknown or partially known. So you have a model, but maybe not a good model. You know it's not an accurate model. And the whole system is subjected to disturbances that also are usually unknown. Wind gusts, for example, right? Or changes in mass of the airplane, you know. And so the goal here is to design a control system. What a control system does, it's also a dynamical system. So this here is the controller, or the control system. And what it does, it takes measurements of the output, Y, through some kind of a sensor. I guess I should put the controller a little bit before. So maybe I'll just put it here. And so it measures the output. Maybe there's a desired reference or a command signal that, let's say you want an altitude of 30,000 feet. So the pilot would dial in this reference. And then it puts out a signal through an actuator, which then moves the control surface. So these are, for example, the hydraulic system that moves the control surface, right? So this is what we design, okay, is the controller. It's also a differential equation most often. And in designing a controller, you want to know something about the process, as much as you know. So if you have a model of the process, this would be a model-based design, right? And some of the most common controllers that you see as, for example, proportional integral derivative controllers or PID controllers. But if you're designing an airplane, they're much more sophisticated than this, right? And so what control engineers do is they worry about this controller design. And one of the first things that they obsess about is stability, right? So the stability issue is the following. So now you're taking a process, which is a dynamical system. It may even be stable to begin with. So it's fixed point, let's say it's stable. And then you're adding feedback. So here we have negative feedback, usually. And now you have a different process because now this closed loop, we call the system closed loop, because now the dynamics include the dynamics of the process itself, the dynamics of the actuator, the sensor, and the controller, interconnected in this way. So this here is called the closed loop system. And before the control, when you just have U and Y, that's called the open loop. Or you just break it anywhere, that's the open loop. Now, anytime you close the loop around a dynamical system, there's a risk of instability, right? Even if the controller itself is stable and the process itself is stable, when you put them in closed loop like this, there's a possibility that the system becomes unstable, okay? So you can get all combinations. So in fact, the process can be unstable and the controller can be unstable, and you interconnect them like this, you could end up with a stable system, and vice versa. So all combinations are possible. So you really have to check. You have to look into the dynamics of each of those parts and formulate the dynamics of the closed loop, and then let's say looking at the eigenvalues of the linearization around the fixed point, and check that all the eigenvalues have negative real parts. Okay? So that's the first thing control engineers worry about, is stability. If you don't have stability, you can't really begin to talk about performance. But another thing that you want to do, or you may want to do, is you may want the output Y. So here, let's say objective. You want Y of t to go to R asymptotically as t goes to infinity, right? So R here, let's say, for example, is a constant. Some constant reference, 30,000 feet. So the pilot dials in 30,000 feet, and then the control system takes over, and you would like Y to be, which is the altitude, to approach 30,000 feet in the steady state, right? So that's one objective of control. Now, R doesn't need to be constant, so there's a different way of controlling. When you have, let's say you want to track a sinusoid or any other signal, any other command signal, you can also do that. Now, in designing control systems, what control engineers worry about, other than stability, is, so here's time, and this is the desired value, right? So Y, which is the output, you want it to go to, in steady state, to, let's say, R. There are various ways to get there, right? So you can have a system that approaches it very, very, very slowly, like this. Or there's a possibility that it goes like this, right? Or there's an optimal behavior, maybe it overshoots a little bit, and then it converges to the steady state. So this system is very sluggish. This system here is very lightly damped. It oscillates a lot. And this here is close to being optimal, right? So these are transient dynamics. And as a control engineer, you want to design your control system so that they have nice transients, right? They don't overshoot. They're not oscillatory like this. They eventually reach the reference. And they have other properties, right? And all of that you have to ensure after you have ensured stability. You can do this in many ways. So control engineers also do this in an optimal way. You can set up an optimization problem and solve an optimal control problem to tell you what the best behavior is. And now you're trying to do this in a scenario where the process is not fully understood, right? So there's a lot of uncertainties here. Also, you have disturbances that you don't necessarily know about in advance. Okay, so in a nutshell, that's what control theory is about. And what I would like to tell you today, essentially one or two ideas. The first idea is that negative feedback is actually, or the main reason why you have negative feedback is to get robustness, okay, which is the reason why it's used in biology. And I'm going to give you some examples of that. So negative feedback for robustness. The second idea is that you can use negative feedback to change the dynamics of the process, right? So if you have a process that has a certain dynamics, you can actually alter these dynamics simply by using negative feedback, okay? So those are the two ideas I would like to show you today. That's all we have time for. And we will start with essentially, I'll spend a lot of time on linear systems, but the same ideas will also apply for nonlinear. It's just easier to explain here. Okay, so let's go back about 100 years in history and look at one example of negative feedback. Is it okay to use this part of the board for the cameras? I guess. Yeah, just let me know if otherwise I could just erase this here. So about 100 years ago, there was a problem of establishing telephone lines. You know, telephony was just being discovered and implemented, and to have long-distance telephone lines, engineers need to boost signals so that they can travel across the Atlantic, but also inside the continent. So essentially, in order to boost signals, you needed amplifiers, right? So let's say an amplifier is simply a device that takes an input, let's call it here X, and let's say the output Y, and just in its very, very basic form, in steady state, so Y is equal to A times X. Okay? Just simple number, multiply X by a number. And A is generally large, in the tens of thousands, hundreds of thousands. And at the time, this is basically in the, let's say, 1910s or so, they had vacuum tubes. All of you are young people here. You probably haven't seen a vacuum tube. Maybe you've seen it, but so these, they're kind of little, about this big. They're made out of glass, and the idea is that they amplify signals, and it takes a while to warm up. The old TVs had vacuum tubes in them. They look something like this. And then you would install them in your electronic circuit, and then if you wait long enough, it starts amplifying. The problem with vacuum tubes is that they had variable gain, and they had a lot of nonlinear distortions. Okay, so imagine if you're trying to build an amplifier for a voice signal, the variable gain actually created a lot of distortions. And so you can get high gain, but A is wildly variable. And so that was the main problem, that these engineers, electronics engineers at the time, were trying to solve in order to establish long-distance telephony. Then the problem was being worked on by this engineer called Harold Black, an American engineer. And in a stroke of genius, in 1927, he got this idea, which now we see a very simple idea, but at the time it was actually a revolutionary idea. And he got this idea while he was on the ferry in New York to say, okay, well, what if we can take the output, measure the output Y, and then, let's say, feed it back to the input in a negative phase fashion. So here this is minus, and now this is the input U, okay? So you measure the output, you multiply it by some constant, and then you subtract off the output from U, and then you feed that into the amplifier, okay? So this was the birth of the negative feedback amplifier. So let me just write this here. And the person was Harold Black. And when he did this, it solved the problem almost instantly. right? So the system was very robust. All these variations in A no longer made a difference. There was a lot of improvement in the distortion, so the system was behaving much more linear than it did before. And it turns out, with this simple idea, the telephone lines, or at least the amplifiers, could be extended for thousands of kilometers. So why does that work? Well, I'm going to show you, just give you a very simple reasoning, right? And the reason this works is the same reason why negative feedback is so useful for robustness, right? Why you see it everywhere. It's a very simple idea, but an extremely powerful one. So before, what do we have? So we have y equals a times x. And now what we have is x is equal to u minus beta times y. Okay? So now let's plug in for x over there. So here we have y equals a times x is now u minus beta times y. And I'm doing all of this in steady state. I'm not looking at dynamics and so on, which you can do. But this is much easier. So I'm assuming everything is in steady state. And so you see here y is on both sides. I can take this to the other side here. So I have 1 plus a times beta times y is equal to a times u. And so y is equal to au divided by 1 plus beta times a. Okay? So this is now the new y. Compare this to before, where you just had a. Now, if you look at this, you remember a can be very large but variable. Okay? So if a times beta is much larger than 1, so this here is approximately equal to, so if a times beta is much larger than 1, you have a times u divided by a times beta, which is equal to 1 over beta times u. So here this is for a beta much larger than 1. And voila, we don't have any dependence on a anymore. Okay? We have dependence on beta, but beta doesn't need to be large. In fact, for a high amplifier, you need beta to be small, and you can implement this with precision elements. Right? So you've actually used the fact that A is high gain, and you've traded the high gain in for robustness. Okay? So usually negative feedback systems always have an expression that looks like this. And if the denominator is large, the numerator here cancels, and you just have 1 over beta times mu. So this is really the key idea why feedback gives you the robustness that it actually does. And it's demonstrated here very simply with this amplifier. Modern day amplifiers work this way. I don't know how many of you work with electronics, but one of the most commonly used operational amplifier is called the MUA741. So every amplifier, every manufacturer, every electronics manufacturer makes a version of it. And essentially, it looks like this. So one implementation of it looks like this. So this is the output. This is ground. So here, this is the out. And then you have 2 resistors connected in this way. This here is the input. So this is V in, and that's V out. So here, this is R1, that's R2. So this amplifier provides the gain, but again, its gain is largely varying. And just by designing R2 and R1, 2 resistors, actually minus R2 over R1 is the gain, minus R2 over R1. And these are resistors, so you can make resistors with very high precision, and that determines the gain of your amplifier, right? All the complexity is sitting here. You get the amplification from this operational amplifier, and then simply the user just chooses 2 resistors that determine the gain. So this gain is like this reference, right? Otherwise, the system will be robust to variations in the amplifier gain. And you really don't want a system that's robust to everything, right? You want to be able to tune the gain, for example, right? To dial in different gains. So in this case, this system is not robust to the ratio of R2 over R1. It's only robust to the gain itself. And that's exactly how it should be, right? Okay, anyway, so any questions about this amplifier example? All right, I'm going to give you now to switch over to another example where actually this robustness is taken to the extreme. Okay, at least at steady state, it's taken to the extreme. So let me do this here. So we'll start with, let's look at an example of a car. And I think you've all seen cruise control, where you can control the speed of a car. You can dial in the speed that you would like to be driving at. And then the cruise control will take care of maintaining that speed in spite of the different inclines and so on. I'm going to look at a variation of this problem. And in this case, I don't want to control the speed. I want to control the position. Right? Just so suppose you have a car model here. Mass m. And I would like to control the distance from a particular reference point. So this is my reference. And I can apply a torque to the wheels. Okay? So I have a force, F, that's equal to tau over R. R is the radius of the wheel. And let's say I have also, as a car is moving, there's a viscous friction term that goes in this other direction. And that's proportional to the velocity usually, depending on the speed. Sometimes for higher speeds, you don't have a laminar friction, you have more turbulent frictions, in which case you have to look at V squared. But let's just, for simplicity, look at laminar drag, so K times V, which opposes the, sorry, not V dot, X dot, which is V. And we also have some unspecified disturbance here. So this disturbance could be a force that's due to an incline, for example. If you change the incline up or down, this D could be positive or negative. And I would like to write down the equations of motion for this car and to be able to control X. Okay, to see how I can control X. And the idea is I would like to measure something. So following the control scheme, I measure X, and then I use torque as my input. So let's say I have control over the torque in the tires, and then that's what I would use. Okay, so let's write down equations of motion. So the mass times the acceleration, which is mx double dot, is equal to the force, which is tau over r. And so here minus k times x dot, and then plus d. Okay, so these are the equations of motion. And I have now two state variables. And those are x, the position, and v, which is the velocity, right? So this here is the position. Okay? All right. So I can write the differential equation in terms of, if I can convert this into a first order or system of two first order differential equations. So here, x dot is equal to v. That's the velocity. So that's my first state equation. And v dot, which is x double dot, that's this thing here, is minus k over m times v. And then I have here plus tau over mr, and then plus d divided by m. Right? So I have minus, yep, that's correct. So it's tau over r, and then d over r. Okay, so these are my dynamic equations. Okay? Now, it's a linear system, so it's easier to analyze. And so essentially the way you can think about this in the block diagram that I showed you before, so here are the dynamics of the car, and here x is the output. That's what I want to control. If you want to control the speed, you want your speed as your output, right? But here you have v. But here we want to control the position, and tau is the control input, okay? And I want to design a controller by essentially coupling the output. So here's some reference, and that's my controller. Okay? All right. So what could we do? How could we build a controller like this? Well, one way to think about it is that, let's say I would like my x to follow a reference. Okay? So we want x of t to go to r. R here is constant, some constant position, as t goes to infinity, right? So asymptotically, we want the position to approach r. Okay, well, there are various possibilities. We're going to start with the simplest possibility. Well, if you don't use a feedback controller, you could try to do it open loop, right? But that's kind of very more challenging because essentially you have to pre-compute the input that will actually move the car enough distance so that your x is equal to r. And well, that's not necessarily hard to do. The computation is not, you can come up with the input profile that will do it. But then this is going to depend on everything. It will depend on r, getting r exactly, and it will depend on the mass being exact, and you change any of these variables, and that you don't have friction, knowing the d. And if you change any of these variables, of course, your x will be off. But we can do much better than this. So let's start with a very simple idea, which is what's called proportional feedback. That's the simplest possible feedback you can apply. Okay, so how do we do proportional feedback? Well, let's define what the error is. So the error, E of t, we're going to call it r minus x of t. Okay, that's the natural definition. We want the error to go to 0. And so for proportional feedback, just says, all right, well, let's apply tau to be some constant, some proportional constant times the error. Okay, simple as possible, right? You calculate the error, you feed it back, multiplied by a constant. Okay, well, let's see what happens when we do this. I can just go back to the equations. So x dot equals v, and then v dot is equal to minus k over m times v is still there. But now I have kp, instead of tau, I have kp times r minus x divided by mr. And then I still have my v over m. Okay, so these are the dynamics now. Notice that they've changed because now we have x here, whereas before we did not have x. Okay? So one of the things we have to worry about is the stability. So we have to check that this closed loop system is stable, that we somehow didn't stabilize it by just simply doing this feedback. Now think about this as a dynamical system. We can look at its fixed point by setting the left-hand side to 0. We can calculate the fixed point. But for stability, we need to compute the Jacobian, okay, and look at its eigenvalues. And in this case, it's a 2 by 2. So here, let's just see here for stability analysis. The Jacobian, in this case, we'll call it the A matrix. It's just easy to write down by inspection. So here we have 0 times x plus 1 times v. So I have 0 and 1 here. And in this case, we have minus kp over mr for the coefficient of x. And here, coefficient of v is minus k over m. And that's my Jacobian matrix. And so I can calculate the eigenvalues, which are the roots of the characteristic polynomial. I'm using these terms because I'm going to be using them further on, later on repeatedly. So here the characteristic polynomial, I'm just call it d of lambda, delta of lambda, and it's equal to the determinant of lambda I minus a, which is equal to the determinant of lambda minus 1, and here we have plus kp over mr, and over here we have lambda plus k over m. Okay, and it's a 2 by 2. I can calculate the determinant easily. So this is lambda times lambda plus k over m plus kp divided by m times r. Okay, which is equal to, it's a second order polynomial, k over m times lambda plus kp over mr. I don't know if the camera can see this, but essentially we have a second order polynomial here. And if you calculate the roots, it's clear that because this term is positive and this one here is positive, that the eigenvalues are going to have negative real parts, and so this system is going to be stable as long as kp is positive, right? So if kp is negative, then the system becomes unstable. So we need negative feedback, not positive feedback. So remember here, so we had kp times e. So e is defined with a minus sign here, so this becomes minus kp times x, therefore negative feedback. So in this case, as long as you pick kp positive, there's no way you can destabilize the system. So we're in business. Okay, good. So now that the stability is taken care of, what about the performance objective? Does x actually equal to r? Well, let's see. We look at the left. We set the left-hand side to 0 and see what we get. So I want to look at the steady state. So at steady state, well, what will happen with this type of control system? Well, v will be 0. V is equal to 0. And then the second equation tells me what r minus x is going to be. So because v is 0, this will be 0. And then r minus x is going to be, so that's my error. So r minus x is equal to minus d. So we have m. We can cancel the m on both sides. Minus d times, so this goes to 0. This becomes minus d times r over kp. Right? Yes. Okay, so this is my steady state. Yes?
I missed a part of it, but you said that the eigenvalues are positive.
No, the eigenvalues are going to be negative in this case, right? So these are positive. So you can just apply the characters, look at the roots of the second order. And for a second order polynomial, necessary and sufficient conditions are all the coefficients have the same sign. And in this case, they do. So this is the steady state error. And you can see it's anything but 0, right? So you will never get good tracking with a proportional feedback controller. If you have any disturbance, depending on what r is and what kp, you will not get a steady state. So if you have a slight incline, you will have a steady state error. Okay, so that's not, I mean, it works. What you could try to do is you can try to make kp large, right? So kp, remember, is your design parameter. If you make kp large, this can be small. It won't be 0, but it will be small. The problem with making kp large is that if you make kp large, then some of the eigenvalues will become complex. And so here's a complex plane. And so here, the eigenvalues will have large complex parts, which basically means your system is going to be oscillating, right? So complex eigenvalues for a linear system means that the response is going to be oscillating. And then the larger Kp is, the higher the frequency of these oscillations. So that's not really good either, right? So you can't make Kp too large, but if you don't make Kp too large, then you have to deal with a constant steady state error. Okay, yeah? So non-zero steady state error. So what is the solution? Well, here's another solution that is actually quite nice. Let me keep this. And this is a powerful idea that underlies a lot of the structure of a lot of control systems, including those in biology, as we will see later. And so this is called proportional. You augment the proportional feedback with integral feedback. Proportional integral feedback. Okay, so what does that mean? Well, it means you take tau, and tau is now, you still keep Kp times the error, and we'll see why we want to keep that term in there, E of t. But now you add Ki times the integral from 0 to t of the error, E of tau d tau. Okay? So that's why it's called this is the integral feedback. That's the integral term. Okay? That seems weird. Why do you want to integrate the error instead of just taking proportional? Well, you will see in a second. Actually, it really changes the dynamics in a very nice way. So now, if I write down the dynamics again, so I have x dot equals v, still it hasn't changed. V dot is minus k over m times v. And now plus, I still have Kp over mr with times r minus x. But then I have another term, which is Ki over mr. And instead of x, I have this integral term. Let me call this whole thing, I'm going to call it z of t. I will introduce this as an additional state variable. So now I have a third order system, right? And I still have my disturbance, d over m. So now I've introduced z that way, I have to add a third equation. So z dot is equal to e, but e is r minus x. So now this is my system dynamics, right? It's more complex a little bit because I've added a third state variable. All right, let's do the stability analysis, and then we will see the effect of this integrator, putting this integrator in feedback. Okay, so now the Jacobian is going to be a 3x3 system now. So I have, as before, 0, 1, 0. So I have 1 here and multiplying v. And now for the x, I have minus Kp over mr. That's the coefficient of x here. And for v, I have minus k over m. And for z, I have 1. That's this one. Oh, sorry, I have ki over mr. Okay, and this is a constant, so that doesn't matter for the Jacobian. And for z dot, I have negative 1 here, 0, 0. So that's my Jacobian. And I can calculate the characteristic polynomial. Let's look at d of lambda is equal to the determinant of lambda I minus a. So we have lambda minus 1, 0. Here I have kp over mr. Here I have lambda plus k over m. And here I have minus ki over mr. And over here I have 1, 0, and lambda. Okay, so that's the lambda I minus a. And I just can calculate this determinant. It's not too bad. It's got my zeros. So here I have first term lambda. Here I look at the determinant of this minor. So here I have lambda times lambda plus k over m minus 0. And then I look at here, so I have minus 1, but I have to change the sign. So I have plus 1 times the determinant of this part, which is lambda times kp over mr. And then minus ki over mr. So here plus ki over mr. So that's my characteristic polynomial. It's the third order polynomial. So lambda cubed plus k over m lambda squared plus kp over mr times lambda plus ki over mr. Okay, so that's it. Now I need to have this characteristic polynomial have all of its roots in the left half of the complex plane, so it has negative real parts. I don't have a formula. Well, there is a formula, but I don't have it on top of my head, and anyway, it's not really, it's too complex to worry about. But here's what I know about third order polynomials. So for third order polynomials to have all their roots in the left half of the complex plane, first of all the coefficients must have the same sign, and they do. They're all positive, but that's not enough. That's only a necessary condition. The other condition is that the product of these two coefficients must be larger than the product of these other coefficients. So where does that come from? That comes from something called the Routh criterion. Okay, so the Routh-Hurwitz criterion. So you have to trust me on this. Otherwise, you can just compute it for some values. So for stability, you need k over m times kp over mr must be larger than 1 times ki over mr. Okay, that comes from the Routh's test. Okay, and you can look it up if you want, but essentially that's what the condition is, right? So, all right, I think that's fine because I have control over ki and I have control over kp. I don't have control over k. That's the viscous friction coefficient. But I know if I make kp sufficiently large, then this condition will be satisfied, or ki sufficiently small, right? So that could be a design criteria when I pick my two constants. And so stability is not an issue here either. Okay? All right, but now here comes the big payoff, which is when we look at steady state. All right, so here, actually, it's all in front of us. So in steady state, I'll use this color. V will be equal to 0, and then Z will be also equal to 0, so this term will be 0, and R minus X, so this will be satisfied, that D will be satisfied this equation. Sorry, Z will not be 0. Z will be something that is needed to satisfy this equation, but the important thing is here. Okay? R minus X will be equal to 0. Okay? That is the effect of the integrator. And notice that R minus X equals to 0, that's our condition, right, at steady state, will hold regardless of what Kp is, regardless what M is, regardless what R is, regardless what Ki is, and certainly regardless of what D is. And even if I have additional dynamics, like if I have fifth order system, if I'm ignoring some other dynamics, let's say infinite I mean, the car is an infinite dimensional system, right? It has a lot of bending modes and so on. If I include them all in here, right, it doesn't change this fact, as long as the closed loop system is stable. Yeah, so at steady state, and this here is the really the payoff. Let me just write it here. Steady state, R is equal to X, okay? So that's because, that's due to integral feedback, yeah? So I'm stable, I have the desired steady state property. And again, as I said here, this is independent of the other parameter, of system parameters. That's why control engineers like this integral feedback, because it gives them this kind of property without having to know the dynamics exactly. Okay, so essentially our problem is solved. But before going to the next step, I want to show you an alternative. By the way, are there any questions? Yes?
Does it work if you remove the proportional part?
Oh, yeah, what happens if we remove the proportional part? That's a good point. So if Kp is 0, I get this term to be 0. And then the characteristic polynomial will no longer have its roots in the left half of the complex plane. So Kp is 0 is actually, Kp non-zero is necessary for stability, not for this property. Yeah, good question. Now, while we're here, so one thing I don't like about this equation is that this term here depends on K, the coefficient of viscous friction, which could be very small, typically is. Like if you think about low speeds in air, this is not going to be a big term. So this is not 0, but it's almost 0. I'm relying on it to determine the eigenvalues of my system. So one way to avoid that and to improve the performance of the system is to do the following trick. So what you do here is you still keep proportional integral feedback, but then you add to it a derivative term, okay? So here, proportional integral derivative feedback. And so I'm going to keep this, and so I will add plus Kd times the derivative of the error. The derivative of the error, so the error is R minus X, so that's basically minus Kd times V, right? Because the derivative of X is V, and I have R minus, R is a constant, so that's 0. So basically I have another term in my equation here, which basically looks like this term, but instead of having minus K over M times V, I have minus K over M minus Kd times V. So the characteristic polynomial becomes, this is for a PID controller, proportional integral derivative, it becomes lambda cubed plus K over M plus Kd over M, right? And everything else is the same. Lambda squared plus Kp over Mr times lambda plus Ki over Mr. Okay? So this is very nice. The reason why this is very nice is because I can specify all coefficients in my characteristic polynomial. Right? I can certainly make sure when I choose them that this is going to be stable. And actually adding the Kd here is more stabilizing for my dynamics. Because remember, this condition here, instead of K, now I have K plus Kd. So I make this left-hand side, or this part of the inequality, even larger. And so that's why you hear that derivative control is usually stabilizing. This is one reason. right? But then, because I can pick KD, KP, and KI independently, I can pick any characteristic polynomial I like. And I can shape the performance in any which way I like. And after all, the transient dynamics of the system is determined by the eigenvalues of the Jacobian. And in particular, so here the response, the system response, so this is x of t, that's the vector, that's the state, actually is a linear combination of, let's say here, v1 e to the lambda 1t plus v2 e to the lambda 2t plus v3, so alpha 3, v3 e to the lambda 3t. The lambdas are the eigenvalues, and the v's, these are the eigenvectors corresponding to those eigenvalues. So for any initial condition, the response of the system looks like this. And since I can pick the coefficients of the characteristic polynomial any which way I want, I can place the eigenvalues anywhere I want in the left half of the complex plane. And therefore, I can shape the dynamic performance any which way I like, because that's dictated by these exponentials. These are going to be decaying exponentials. Yes?
Isn't the derivative term a problem if you have a noisy system?
I'm sorry?
If you have fluctuations,
yeah.
Isn't the derivative part of the controller?
Yes, that's a very good point. So the question is, very good question, is that if I have a noise in my system, then let's say if I have sensor noise, and I'm actually taking the derivative, where is this? Yeah, I'm taking the derivative here of r minus x. So if my measurement of x is noisy, then I'm basically differentiating noise. Well, there are two ways to get around this problem. One way is to add a low-pass filter first before you differentiate. And that's typically what is done. Nobody ever implements a pure differentiator. But in this case, I have an even better solution to solve this problem. And that's the following. So instead of taking the output measurement of my system and differentiating it, I already have x dot is the velocity. So instead of actually differentiating the position, I just feed back a measurement of the velocity. And the measurement of the velocity itself is not noisy, right? That's just you just have an actual sensor for the velocity. And I use that in place of x dot. Okay, so I think this pretty much completes this part. So now you've heard of PID controllers, proportional integral derivative. You can think of this in the following way. You're adding a combination of three things. This measures the current error, right? The present. This here is a measurement of the past because you're integrating the error in the past, right? And the derivative is like an anticipatory process. So this here like your anticipation or your expectation of what the future error is going to look like. So you look at the current value of the error, the past value of the error, and your prediction of its future value. You take a linear combination of these things. That's what PID controllers do. And I would have to say 95% of all controllers in industry use PID controllers. And the reason why they use them is because, well, there are just three parameters. It's easy to tune. You don't even need a model. So you can build this and just play around with the parameters and see if you get good performance. And that's what often happens. Now, that's not what we teach our students. We want to do model-based control. We want to derive the dynamics and see the effect. Certainly, there are much more sophisticated controllers out there for advanced operations. But really, PID, you know, it's in your chemostats. It's in your, I mean, many of the devices that you use today have just simply PID controllers. Okay? Any questions about this? So now I can use the PID parameters. I can get away with PI. I cannot get away with I by itself, and I cannot get away with P by itself. If I use I by itself, I don't have stability. If I use P by itself, I have stability, but I don't have zero steady state tracking error. So the minimum I can get away with is PI, proportional integral, and the D just improves the performance even more, right, without losing the tracking property. Okay. All right, very good. So now I want to show you how this works. So I've actually built a car that specifically for this purpose. And this is Lego, so you can buy this for about $200 this is an old model. I built it, so now they have newer models of these things. So what this does, so I have this has an ultrasonic sensor. It transmits sonic waves and measures back the time delay and uses that to estimate the distance. So it's exactly this problem, right? And I can control the torque. I can program it in. And this has encoders, so also for the wheels, right? So I can measure the velocity if I want. And then this is my main measurement, which is the position. And I've set this so that the reference value is 30 centimeters, right? So R is 30 centimeters. So I use this kind of feedback, proportional integral derivative. This is just to improve the performance. Actually, I don't remember if I even use, yeah, I think I do. Anyway, there are different versions of it. You can try to see what happens. So now I'm going to show you how this can keep a distance of 30 centimeters with anything in front of it. I have to turn it on first. Okay, here it is. Let me make sure it's there for the camera. Okay. And then it goes back. It's now 29, and then it should go back a little bit more because the integration, 30, okay. Yeah, 28. And then it's 30. So if I can't lift this table, and normally when I do this demonstration, I lift this table by 45 degrees, just to show that the disturbance actually doesn't affect it. But I don't have that thing here. Yeah. Now I could change the wheels, and I don't have, well, I do have some other wheels. Let's see. Just a second. I usually have bigger wheels, but I forgot those in my hotel room. The bigger wheels actually do much nicer. These are smaller wheels. But the idea is that it shouldn't make a difference to the steady state. But it will make a difference to the transient, because the transient dynamics depend on the eigenvalues, and the eigenvalues depend on R. So let's see what happens. And these aren't much bigger, they're just a bit smaller. So I expect maybe this would be even more sluggish. The other ones are bigger, so it would actually make the system run much faster. Okay? Yeah. Yeah, it's even slower. You see, it takes a bit longer. The other ones are much more fun, actually, yeah? So there's no overshoot here. Yeah, it's too bad. Yep, 20, 29, 30. Yep. Okay, so anyway, that's the demonstration for this. All right, let's now switch gears to something else. Let me first look at the time. How much time do I have?
About 30 minutes.
30 minutes. Okay. I wanted to do one other example to show you what control systems can do, and that's the following. And then I'll switch to the biological case. And by the way, this idea of integral feedback, you can also apply to nonlinear systems. There's nothing in here about the linearity of the equation. As long as your fixed point is stable, then if you have an integrator, you should still get this perfect adaptation idea. Okay, so let's look at a linear system again, just for simplicity, that I would like to control. And so I have a system here. Let's say here an input U and an output X. X could be multivariable, so it could have multiple inputs. So basically, typical linear systems look like this. X dot equals AX plus B times U. This is where the input is. And this is a state vector So here this x is n by 1. So I'm assuming I have n different state variables. So the matrix A it will be n by n, usually real. This here, depending on how many inputs you have, this is n by m, but let's assume we have a single input instead of multiple inputs. Otherwise, you can have multiple inputs, u1 up to um, and then this becomes n by m, but let's keep it simple, right? One input, n different states, okay? So that's a linear system. Okay, so we say this system is controllable, okay, if you can steer the state from any initial state to any final state. So let's say here this is x1, this here is xn, this is the state space, call it x1, x2. I guess this is x, what do I call it, x2 or xt. Yeah. So let's take, you take two states in the state space, and the state space here is Rn, but I'm assuming n is 2 here. If you can find an input, remember, so this is the initial condition, at time 0 you start here, and now by applying the input, the state moves around. So if you can find an input that will steer the state from some any initial condition to any final condition in finite time, okay? So that's called controllability. Okay, so here, controllable, if there exists u from 0 to t1, so u of t, yeah, defined from 0 to t1, so that the state moves from x1 at time 0 to xt at time t1. Or let's say xt1 at time t1. Okay? So it's a very natural concept, right? Controllability means you can steer from anywhere to anywhere. It turns out that if you can do this, then you can do it in any arbitrarily short amount of time. So if there exists a finite time that allows you, if you can find an input that will allow you to go from x1 to xt in time t1, then you can find another input that will take you from the same initial condition to the same final condition in any other amount of time. It could be arbitrarily small. Okay? One can show this. But the important thing here is that there's an algebraic condition for testing controllability of a system like this. Okay? And I'm going to give it to you now. And it's a very, very simple condition. It involves checking the rank of one matrix called the controllability matrix. And that's very nice. And let me just, I'm going to state the theorem. There's no way we're going to have time to prove it. But if you want, I can show you after class. You can ask me, and I will show you how to prove any of these things. So the following are equivalent. And I have actually two theorems here, but I'm going to compress them into one because of lack of time. So 1, x dot equals ax plus bu is controllable. Okay. 2, the matrix B, AB, A squared B up to A to the n minus 1B has full rank. So in this case, because we're taking single inputs, B is n by 1, so this matrix is square. So I could say it's invertible or it's non-singular, right? So all you have to do is just form this matrix and check the rank or check if it's invertible. Look at its determinant in this case. And if its determinant is equal to n, then the system is controllable. Otherwise, it is not. And the third thing, which is also very interesting, there exists a transformation a linear transformation x equals to tz, so t is invertible, such that in this new coordinate system, z dot is equal to a bar z plus b bar u. So if I make this transformation, t is invertible, then I can look at the transform system in these new variables. I haven't really changed anything. But the A matrix and B matrix would have changed because of this transformation, such that now A bar has a very special form called companion form, and it looks like this. So you have 0 here, 1, zeros everywhere else, 0, 0, 1, 0, and so on, until 1 here, and then here, 0, zeros. And then at the last row, we have, you probably can't see this with the camera, I don't know. You have minus A0, minus A1, all the way up to minus AN minus 1. And what these are the coefficients of the characteristic polynomial of the matrix, right? So that's the A, and the B bar looks like this. It has zeros everywhere except 1 in the last position. Okay? So here, minus A naught, minus A1 up to minus AN1. So here, this is, maybe I'll just write this as a note. Characteristic polynomial of A bar is actually this one. A minus 1, lambda n minus 1. That's where these coefficients are. Plus, By the way, you can check this very easily. Take a matrix. This is called a companion form. Take a matrix like this, square matrix, which has this structure. Look at the determinant of lambda I minus A, minus A bar, and this is what you will get. Okay? So anytime you have any matrix in this form, you can write down the characteristic polynomial just by looking at the last row. And B has zeros everywhere except for 1 here. Okay, so this is the main theorem that you have. If you have controllability, you can transform your linear system to a system in this called controllable form. Right? Why is this important? Okay, well, this is easy to check. Now, this form is important for the following reason. Suppose I have a system that is in controllable canonical form, and I can take any controllable linear system and put it in that form just by change of variables. And here's what I can do. I can use state feedback. So x dot equals ax plus bu. Okay, I'm going to here suppose in controllable form. Okay, so what I do is I take, let u be equal to, I can take my input, I measure the state variables, x, and I multiply them by a constant, each one by a constant. So I have u is k times x plus v. Now my input is going to be v instead of u. So this is it's called state feedback. That assumes I can measure all my states variables in real time. Okay. You may not be able to always, but there are ways to estimate them and then do this. So when I take this, then my system looks like this. X dot equals a, x plus b times this here, which is kx plus v. And then that looks like a plus b times kx plus b times v. So this is my new linear system with the state feedback. It's the same as before, except I have now a different A matrix. Okay? With state feedback, I have A plus BK. All right? Okay, why is that important? Well, let me show you why. And then we will move on. So I'm not going to spend a lot of time on this. I just want to show you what happens when you have a controllable system. Okay, so here's my A. Remember, A has a companion form, 0, 1, 0, 0, 0, 0, 1, 0, all the way up to 1. And here I have minus A naught, minus A1, minus AN minus 1, rather. Okay, plus, and my B matrix looks like this, and has 1 in the last entry. And then the constant looks like this, K1 times Kn. That's my state feedback matrix over here. So I have n state variables. Each one of them gets multiplied by a corresponding constant K. So that gives me this row. Okay? Now you see the effect of state feedback. Now this is also a matrix which has zeros everywhere in the first n minus 1 rows. The only place where this is not 0 is in the last row, where you have K1 up to Kn. And those get added over here. So here I'll have minus A. Okay, let me just write it down. It's important. 0, 1. So the matrix still stays in this companion form. But then the last row becomes minus A0 plus K1. And so on up to minus A n minus 1 plus Kn. Right? So now hopefully you recognize the importance of this form. Now this is still in companion form. So the characteristic polynomial of the new A matrix is now given by these coefficients. And if I can control K1 up to Kn independently, I can change my characteristic polynomial at will. Right? So here can choose K1 up to Kn to get any characteristic polynomial. Okay, that I want. In particular, if my A matrix to begin with, my dynamics are unstable, so I have some eigenvalues in the right half of the complex plane, I can find K's so that with the state feedback, all the eigenvalues will be in the left half of the complex plane, and therefore the dynamics are stable. So with state feedback, I can stabilize the dynamics. And all I have to do to be able to do this is my initial system has to be controllable. And basically, unless you do something foolish, any system that you build is going to be controllable. So if you pick an A and B matrix at random, for example, they will be controllable with, the uncontrollable matrices, A-B pairs have measure 0. It's of course, that doesn't mean it won't happen. If you want, you can easily rig your system so that's unstable. So for example, if your input doesn't have access to other second state variable and only has access to the first variable, then that's not going to be controllable. But generally, this rank condition will be satisfied. Okay, so now you understand regardless of what your initial dynamics are, if you can do full state feedback, then you can change them to anything you want. In particular, you can make an unstable system stable. All right, before going on, I just want to show you some of the applications of this. And I really want to go to the biology part. So again, imagine if you have a robot that has, let's say, a wheel that's attached to a body. Okay. And let's say here we can apply a torque, again as before, tau. This maybe has radius r. And you look at this angle as being theta. Okay. One can look at the mass m of the body You also have the mass of the wheels. You can have the inertia of the body, moment of inertia. And then you can have the inertia of the wheels. Let's say, what else? So we can also have friction over here. And you also have friction at the axle here. Axle friction, right? So one can write down a dynamic model for this using Lagrangian mechanics. And you can clearly imagine, you don't need to write the equations, but you can imagine that in the upright position, this is an unstable system, right? Because you move it, there's clearly a fixed point there, but it's an unstable fixed point. Now, this thing here can be linearized, right? And then you have x dot equals ax plus b tau. Tau is the torque. And the state variables x, in this case, they're actually phi, theta, phi dot, and theta dot. Okay, so what is this here? This is the wheel angle. This here is the, well, I already defined this one. This one here is the wheel velocity, and that's the velocity here. So you have this is a fourth order system, dynamical system. These are the state variables. I can linearize it, and when I say linearize, what I need to do here to linearize, basically I take sine of theta to be approximately 0 at that fixed point, and then cosine of theta approximately 1, okay? And theta dot squared approximately 0, right? The velocities are small. So with these approximations to the nonlinear dynamics, I will get a linear system like the one I showed you, okay? You don't have to do it that way. You can write down the ODEs, you could write the Jacobian, and that's what you will get. You will get whatever is equivalent to this. It will be a linear system. And now this system can be shown to be always controllable, okay? Therefore, I can always measure x, feed it back to tau with the right parameters. So I basically measure the wheel angle, the wheel velocity, the angle of this, and the velocity of that, and feed it back. And I should be able to stabilize the dynamics, right, of this system. Okay, well, I have a demo for that also. So this is a robot that I built, also from Lego. And, oh, it needs the wheels. Okay, let me get the wheels back. Okay, put the wheels back. And what this does, so I can measure the position here. The encoders here, I can do a derivative of the position with a low-pass filter to get the velocity here. And here I have a gyroscope which gives me the velocity. And from that I can get the position also, right? So I have the 4 state variables. And I can multiply each one of them by a constant, feed that back to the torque on the wheels to get. All right, so let's. I've actually also built a remote control for this so they can talk to each other with Bluetooth. So it doesn't just stand there, but let's see if that works. I don't really need it to make the demo, and I really shouldn't because of the time. But it's more fun, so maybe you'll put up with a few more minutes at the end. Okay, so now I've established the Bluetooth communication. Now I'm going to actually have these guys. I have to run the remote control program on this. Each of these things are exchangeable. I just have to pick the right program for the right use. Okay, this is the remote. Okay, so now this is working as a remote and it's talking to this guy. Now I have to actually go to the balancing mode. All right, so here it is, right? So this is the gyrobot. And this sensor that I showed you before doesn't do anything here. It just looks like eyes. So it's not functional. And nothing else is functional except that this is just a mass. and everything that's functional is inside here. Okay, so I'm going to see if we can get it to balance. So let's see here. And of course, it's clearly unstable, right? So this is the fixed point, and it becomes unstable. And so let's see if I can stabilize it. I start close to the fixed point because stability is local in this case. I'm doing a linear system, so, and here we go. Okay. All right. So these oscillations, I think because the thing is loose, it was traveling from the US, and then I can make it turn around by moving this. You can make it go forward. Yeah, this really, it normally doesn't oscillate. I think it's just too many modes that are loose, so I need to clip it back together better. Yeah. Let me see if I can. So you can also perturb it a little bit, and it will stabilize. I don't know, but not too much, right? So the thing is, there is a region of equilibrium, right? There's a domain of attraction for the fixed point, and the domain can be larger, but the wheels don't have enough torque. I mean, these are $15 motors, and I've had them for like more than 10 years. So really, one can improve the motor. You can have a bigger region of stability, but it will still be a finite region of stability because I'm only stabilizing around the fixed point. Let's see if I can tighten things up a bit. Maybe it will be a little bit better. Run it again. No. Oh. Yeah. Here it is. Maybe it's a little bit better now. Yeah, that's what's a bit more like it. Yeah. Yeah. And you can also do the incline. You can put disturbances, so it will stabilize here. So this is inclined, so I'm sure it will stabilize. So just have to start it in the upright position. Yeah, there. Yeah. Get back in there. Yeah. Anyway, so that's what you can do with feedback. You can stabilize unstable systems. And with that, I think that we're done with the part that has to do with the board. I want to spend the last few minutes telling you about maybe I have, can I have, so I started 5 minutes late. Maybe if I can go 10 minutes. Can I take 10 minutes? Okay, so we will switch to the slides. So basically what I want to show you is, and this should be enough anyway, I want to show you how these ideas can be applied in synthetic biology, right? So the main thing is that feedback is important for robustness, and we've already seen that in mechanical devices. And now I want to show you, so this is the amplifier example, and you can see that because A is large, the slope of that line is going to be steep, and so if you vary A, the intersection, which is the fixed point, will give you small errors. And now this is very much like this. Without feedback, you have much larger errors. Delta Y is much larger. Now the analogy is a gene feedback, autoregulation in a gene network, right? So in this case, I have a Hill-type negative feedback loop. So Y over 1 plus Yn. Y is the protein output. And that's the transcription rate. Transcription rate is now dependent on Y in this way. So that's clearly negative feedback. And I can use exactly the same trick. I don't have a linear system anymore, but it doesn't matter. I have an S-type curve. It was sort of a Hill-type curve that is steep, right? And I look at the intersection. And again, if you vary transcription or translation parameters, just like in the case of the amplifier, you have small variations in the protein output. As compared to the case where you have constitutive gene expression, there's no feedback. And now if you vary the parameters, you get these big variations in this region, and you get larger errors. So that's why feedback is useful. So cybergenetics, what we mean by cybergenetics, I've actually coined this term because it's much more fun to say cybergenetics than to say systems and control theory at the interface of synthetic biology. And it also is inspired by Norbert Wiener's cybernetics, which basically means the art of steering. But Norbert Wiener did not have genetic techniques that we have today, so we can we can still have some of those tools. So in my lab, what we do is we build feedback controllers at 3 different levels. So we do genetic controllers using synthetic biology methods by applying proteins and RNAs and so on, measuring certain variables and applying the feedback. And I will show you, the only example I'm going to show you is that. So I'm going to use one particular integral feedback at the molecular level. But then we also interface cells with computers, and we use optogenetics. We build these light-sensitive cells that respond to cells. And what you see here is the mRNA, nascent mRNA that's responding to light. And we can target single cells, so we can do single-cell feedback control. And then the last thing is we also do population level. So we have this bioreactor that is outfitted with light so that the cells, we can control gene expression with light in feedback of the whole populations. But I mean, I'm not going to spend much time on the last 2 parts. Okay, I thought I'm in France, so I said this is actually has very good history. The idea that in biology there's a constancy of the internal environment, and this idea was initiated by Claude Bernard, who basically advocated that people should look at the constancy of the internal environment as a running theme in biology as a condition for free and independent life. And then later on, it was picked up by the American physiologist Walter Cannon, who called this homeostasis. Right? So actually, what I will show you here is not exactly homeostasis, but I will show you so homeostasis means you want to regulate a variable to within a certain range. What I'll show you is a stronger notion of homeostasis, what would be called homostasis, if there is such a word. There isn't such a word, but the perfect adaptation that we have seen with the integral feedback is actually homostasis, so exactly the same, right? Not somewhat the same. Okay, so the perfect adaptation idea, you all know about it. We've already discussed it. It basically means tracking with 0 steady-state error. That's all it means. So if you change a variable, in this case, those you see in purple, that's our disturbance. You add a disturbance, then the output goes back to the steady state, right? 0 steady-state error. We've already seen it with the robot, so you're very familiar with this concept. So now we want to apply it to biology. And now we really want to exploit the fact that there's a lot of uncertainty in biology. For example, if you have a network like this, you don't even know the network very often, or you don't know the players, you don't know their interactions. And even if you know them, they change over time. You don't know the external environment, so the external environment could be changing. The dynamics inside living cells are highly, highly stochastic, right? Because so there's a lot of things you don't know. The previous speaker talked about shared resources. So when you share a resource with the cell, you put in a circuit in the cell, it shares the ribosomes and so on, it changes the parameters effectively. So there's a huge amount of uncertainty. But yet we have this concept of integral feedback that is supposed to work in spite of this uncertainty. And so can we actually demonstrate it in a biological context? Can we build a controller? In this case, our controller is going to also be made of molecules. They're also going to be noisy. But we would like it to be stable, naturally. And we want to do set point tracking. So we want some variable of interest, perhaps a concentration of a protein, x sub n, to follow a desired reference, r, just like we have the car following the desired 30 centimeters. So that's what we want to do. And that's called perfect adaptation if it has 0 steady-state error. It's called robust perfect adaptation if it continues to hold in spite of the variations in the network and so on. And we'd like a stochastic theory for that because biology is stochastic. And so, so we want to do all of these things. I'm going to skip that. This is the main slide that will show you actually how this works. So we came up with this motif, which we call the antithetic integral feedback motif, that does exactly that, okay? And so how does it work? So the motif works like this. You have a variable of interest, xn. We build a molecular sensor for it, and you can see that at the top. Z2 is a species, yet to be determined, just some species, whose synthesis rate depends on xn concentration, right? So the more xn you have, the higher the rate of that reaction, chemical reaction, right? Now we have another molecule called Z1 that's produced at a constant rate, which is mu. And so Z1 is the actuator. It basically, the more Z1 you have, it actuates the system at its input, which is X1. Okay? And now the feedback is a very, very simple but important interaction between Z1 and Z2, and it's this annihilation interaction. So Z1 and Z2, annihilate each other jointly. They don't have to actually annihilate. They can just bind together in a way that the complex, Z1 and Z2 complex, is biologically inactive. Okay, so that's what you need. And I don't really need a whole lot. Let me just show you the deterministic version of this. We don't need to look at the stochastic version, although the stochastic version works very well. In fact, it was designed for a stochastic system, but it works just as well for deterministic. So the reactions, we have, it's one reaction here for Z1. And then we have another reaction for Z2, where here you have theta times xn. And then we have a third reaction, Z1 plus Z2 goes to 0 at some rate mu. This is it. Okay? And if I write mass action, let me just write the mass action equation. You see how simple it is and how well this works and why this is actually an integrator. So here what we have this say Z1, little z is a concentration of big Z. So Z1 dot is equal to mu, right? And then I have a reaction here that takes mu away. So minus eta times Z1 times Z2, right? That's from this reaction. Now for this reaction here, Z dot is equal to theta times the output, which is x sub n, right? That's the concentration of the output, minus also an equation which has Z1 times Z2. Okay? So, and of course, I can write other equations that relate xn to the Z1 and so on, the rest of the system. I don't have to, because here's what I'm going to do. I'm going to subtract these equations from each other, and then you have Z1 minus Z2 d by dt is equal to mu minus theta times x sub n, right? And at steady state, assuming the system remains stable, at steady state this is 0, right? So what do we have? Mu minus theta equals x sub n, or x sub n is equal to mu over theta. And that, ladies and gentlemen, is our reference R, right? This is going to be, nothing I've discussed here depends on the network up there. All the thing I need is that the interconnection to be stable. As long as you have a stable fixed point, this particular structure and feedback will ensure that the output of interest is going to go to the reference, mu over theta. And of course it works in the stochastic case. And of course, where is the integrator? Well, Z1 minus Z2, which is a change in variable, a function of time, is the integral from 0 to t of mu over theta minus xn of tau d tau. So that's what this molecular interaction does. It actually builds this integrator. Okay, so, which you can see here. In the stochastic case, this result is true. The expectation converges, right? And not only does the average, population average converge, but also because of ergodicity, which is our notion of stability in the stochastic sense, and I don't really have time to discuss this in detail. Basically what we have at the single cell level, the time average will also converge, okay, for a single cell. The time average will converge to mu over theta, and the population level, as this equation shows, will converge as well. And so here's an example that shows how this is a simulation that x2 converges to the set point. Mu over theta is 3 in this case. You change a parameter, it will still converge. You change any of these other parameters. If you don't have this type of feedback, you just have basic Hill-type feedback, you end up with steady-state error. Because that's like our proportional feedback. There's no integrator. So we've implemented this in living cells. So this was in bacteria where we use sigma factors, sigma W and RSIW. And we use it to control RSC. RSC is the output of interest. So you have this topology that I've described before. And we've also introduced a disturbance just to test that the system rejects disturbances. And this disturbance is a form of MF-lon. It's a protease. And you see that the top curve tells you that with the integral feedback controller, antithetic controller, the steady state is unchanged before and after the disturbance. And the bottom slide shows you that without the feedback, and you introduce the protease, you lose half of the, or 40% of the output. And that's what it looks like in the time domain. You see the time that the disturbance is applied with ATC, you could see a small blip, transient, and then the output goes back to the pre-disturbance level, even though the disturbance is still there, whereas without the feedback, you can see steady state tracking error. And I'm going to skip, also we've done this in mammalian cells, I'm going to skip all of that. Now we're using it for diabetes, and I'm going to skip that. So I just have two or three slides left before I finish, but this is kind of goes to the idea of cybergenetics with light, and maybe connects with one of the talks by one of the speakers later on. So the idea here in this type of control is that if you want to build a controller like this one inside your cell, like the one we've done for the E. coli and mammalian cells, synthetic biology takes a long time to apply, to design things and test them inside the living cells. It could take months or years. So our idea is to take this part that you want to build and then put it in a computer and simulate it using stochastic simulations. And now these interconnections, the observation, you monitor the, let's say, fluorescence of the output that you want to observe, and the actuation is done with optogenetics, with light. Okay? So now you can close the feedback loop, but with your controller that you want to design inside, simulated using Gillespie-type simulations in the computer. So it's still seeing the stochastic interaction. Of course, your cell is, on its own, is very stochastic. And only when you're happy with the design parameters do you start building. Okay, so that's the idea here. And the system we tried on is a transcription system that we built in my lab. So these cells are sensitive to EL222. It is the light-sensitive part. EL222 homodimerizes, binds DNA, turns on gene expression. And what we're observing is a nascent mRNA. And the way we do this, and we want to do this because we want a system that responds quickly, and we also would like to look at the stochastic version. So transcription is very noisy and bursty, as I will show you. And so by adding stem loops to the mRNA and having these stem loops bind fluorescent tags, we can see a red spot, which allows us to figure out how much mRNA is being transcribed. And that's the signal we measure and use for feedback purposes. This is what it looks like for single cells. This is transcription, right? Very, very bursty and very stochastic, right? And then sometimes you go, 20, 30, this is for a constant light input, right? And what you see here on the y-axis, that's the number of molecules per cell. So in some cases, you can see 10, 20, 15, 5, even you can go down to 1 molecule per cell over time. But these are genetically identical cells, and they're responding very differently to the same constant light. Still, our controller should be able to handle this situation because it works for stochastic system on the population average. And so here's how it works. So we can measure single cells. We segment them, track them under the microscope. This is yeast cells. And then each cell will have its own control system running on the computer, which issues for that specific cell its own light command signal, as shown here. And we built a digital micromirror device that allows us to target that light to the individual cells, as you see here. And the last slide I'm going to show you is just a very short movie, and then I will finish. So here you can have single cell feedback. You can try different topologies. So this is the antithetic topology I just described. I just show you the simulation. You can try out dilution, the effects of all sorts of variables, because it's all done in the computer. And only when you're happy with the parameters do you implement them. So here's the video I was promising. On the left-hand side, you see about 150 yeast cells. Now, when I start the movie, these cells will divide, but we're only controlling the mother cells here, so that these 150. And you can see blue light is shining on different cells, different amounts. And on the right-hand side, which you probably can't see very well because the light, you will see red spots. We can quantify these spots. The spots are how much mRNA each cell is producing. And we use that in feedback with the antithetic controller. And the whole point is to show you how you can use this type of controller to control very, very low copy numbers in the cell. So the set point is set to 14 molecules per cell, 14 mRNAs per cell. That's the dashed line here. You see that's the target mRNA that we want. And so can you actually control up to 14 molecules per cell? Well, here's what it looks like. This is the population average being plotted. And what you can see, each cell is getting different amount of light based on its own production. And here, the red spots, well, you can't see them very well. But the average you see here is actually tracking. So you can control up to 14 molecules per cell. And the reason why you want to do that, you want to do control at low copy numbers because of this resource sharing issue that was discussed in the previous talk. Control is not about material energy, it's about information processing. And there's no need to have a large number of molecules if you want to do effective control. You can have 0-1 type, even with one molecule, you can do a good job effectively controlling system. Which is you can control the duty cycle, right? So how long you're at 1 as opposed to how long you're at 0. So in principle, there's no need to have a large number of molecules. And this is good for synthetic biology because as you're sharing resources for the cell, even if your cell, you avoid the issue of mutational escape, right? So if the cell, your circuit mutates, you know, the resulting circuit doesn't grow faster, so it wouldn't take over the population. Okay, so quick summary. Power of negative feedback, very effective strategy for robustness. I showed you antithetic control. And actually, one of the things I didn't show you is that this topology is actually required for perfect adaptation in the stochastic case. So every controller that achieves robust perfect adaptation in the stochastic case must embed within it this antithetic motif. So one can prove this mathematically. And then finally, I think the fact that this is a theory-based synthetic biology, I want to make a case for theory. So thank you very much, and I apologize for running over. Yeah, you have a question over there? Yeah.
So, in the last, in this last controller you proposed, like C1 doesn't seem to be necessarily connected to the network.
Yes. I mean, yeah, I know the question. It's okay. I know the question. So he says, in these equations, Z1 doesn't seem to be connected with the network. Well, Z1 is actually connected to the network, and it affects the stability of the dynamics, right? So without Z1, so you're closing the loop. Z1 here, so Z1 goes on to affect the network through X1, okay? I'm just not writing those equations.
And if it didn't affect the network through X1, how would it change?
Let's go back. This is way, way back there, right? Oh. Right, you see, this is connecting the light in this case, right? And so Z2 is actually measuring something. So if you measuring the output, so if Z1 is not connected, it cannot make any corrections to the output, right? So any deviation in the output cannot be corrected for, and the system, for example, in the case of Z2, will blow up. So you violate the stability conditions. So that's essentially how this would work. The stability conditions have to be met. This is kind of an underlying assumption that you have to show separately. And then once the system is stable, then you can make this argument about tracking. Yeah, you have a question?
Hi, thank you for the talk. And I wanted to ask something about more methodology, I guess. I mean, you're using ODE to, let's say, build the design principles that seems to be robust, at least since you showed us that these things are reliable somehow.
Yeah.
But, I mean, can one translate, since biological systems are inherently stochastic, such a framework to, for example, Markov systems,
Yes.
and write down the equation and find once again similar, or in the best case, equal principles? Is this something feasible, something that we tried? Thank you.
Actually, yes. The answer is yes. And in fact, all of the development for this antithetic controller was done for Markov systems. I'm just simplifying things here. So any controller that works in the stochastic regime, an antithetic controller will, we've shown that it can do that, will also work for the deterministic regime. But so I'm just showing it for the purpose of this lecture. But if you go back to our 2016 paper in Cell Systems, where this antithetic motif was proved, it was all done for the stochastic case. And one other point related to that, there are other integrators that work well that are not antithetic for the deterministic motif. But if you have stochastic dynamics, this is the only motif that will work. And we can prove this mathematically. Yeah, thanks.
So I have just a question about, you said that for Z1 you have a constitutive production of it, like a constant rate of production of Z1. Is it necessary, and how much it should be constant to have a nice control?
So in this case, you can be robust to everything else except two things, mu and theta, because those are the ones that determine the set point. Now, if you change mu, which is the rate of production of Z1, you will change the set point. So obviously, you want to do that. You want to be able to change it. However, the nice thing is that it's the ratio of mu and theta that determines the set point. So let's say you have something like a shortage of ribosomes. And let's say this shortage affects both the production of Z1 and Z2 in the same way, because they're both then the ratio will be unchanged and the set point will be unchanged. And that's a very fortunate thing. That's also something that you can prove mathematically, is that if you want to achieve robust perfect adaptation, there must exist at least two reactions that encode the set point. And in fact, the set point must be some function of the ratio of the two rates of the two reactions. And that's, I think, a good thing, because if you change the temperature or whatever, as long as the ratio remains unchanged, then the set point will be up. But otherwise, there's nothing you can do about it. Your set point will change. Yeah. Okay.
Do you think this method is applicable to society also? For example, controlling panic, or I don't know, stock change, this kind of thing?
I think yes. So if you have agent systems, for example, and you can. So one thing we have done is we have shown that this can work also if you're looking at cells that interact with each other. So it doesn't have to be intracellular, it can be intercellular, where the interactions between cells is such that they produce this type of reaction. So just replace cells with agents, and the same idea should work. So this is one example where we can learn in control from biology, right? So going in the other direction. Yeah.
Any more questions?
Thanks. This is really great. How can we think about inherent limitations in the system, for instance, running out of carbon or things like that? I don't think the theory can inform us on that, right? So in application, how do we think about hitting those limits? Because it's very easy to accidentally run into them in biology.
Yeah. So if I may reinterpret your question, so what would it give if you run out of, I mean, the theory seems like you could be robust to everything, but if you can run out of carbon or something, you know this is not going to work, right? So, I mean, there are assumptions made here, right, which is that the system is stable, right? And that any perturbation that affects the system will maintain the stability of the dynamics. Now, if you have a let's say, a mutation, or let's say a loss of carbon, such that X2 cannot, or X1 can no longer affect the output, because there isn't enough carbon to make enough output. Then the buildup of Z2, so your system cannot keep up. You'll have more and more and more Z1, but you still can't keep up because you don't have carbon, and so you lose stability. So that's where the assumption breaks down. So that is hidden in this one assumption. But as long as you can maintain it, and very often you can, right, stability, then it should work. Now, would these controllers help you? Maybe slightly, because by operating your system at low levels, you kind of postpone the when you run out of these resources, ATPs, ribosomes, or whatever. You don't really need a lot of control. In fact, one can quantify exactly the cost of this controller, and it depends only on mu, not on mu over theta. And so you can keep mu over theta constant. As long as you reduce mu, you can reduce the cost. And you can make virtually zero. And again, just to connect with what I said before, that control is not really about energy or material, it's more about information. So you can transmit information without using up too many of the cellular resources. But whatever you're controlling, if you want to control at this level, there's nothing you can do about that, right? So if you want the concentration of RC to be at a certain value, well, that has a cost with it that is not really mediated by the controller itself.
Okay, I think we should close. We're all hungry. Thank you very much for the great talk.
My pleasure. Thanks.